Welcome back to Tech 240. This is the second video for August 26th. In this video, I'm going to solve the example problem that we set up at the end of the previous video. So I'm going to switch over to the document cam. All right, here is the example problem that we set up at the end of the last video. And we have some givens, because there have to be some things that are given, or else there's too many unknowns. So we were given the value of current and direction of current, the direction and value of current going through resistor 3, and the value and direction of current going through resistor 2. And we're given the values of R1 and R2 and R3. And we're given that ground is down here. So ground is, by definition, 0 volts. All right, so we are going to want to find what is I1, what is I2, what is I3. Some of those we already know. And we are going to want to know what is V1, and what is V2, and what is V3. Also, it's going to ask us what is the value of VL, that's this voltage source on the left, and what is the value of V sub R, that's this voltage source on the right. And a couple last things, it's going to ask us what is the voltage at node A. And the voltage at these nodes is always relative to ground, right? So what is the value of the voltage at node A measured in reference to ground? What that means is, if I have my multimeter, it's over there somewhere, but here are the probes of my multimeter. The black probe is on ground, the red probe is on node A. What voltage do I measure? All right, same thing when I move the red probe to node B. Now what is the voltage at node B? What do I measure? And then what do I measure down here? This one is kind of obvious. You know, this is whole thing's at ground. So if I have my probe here at node C, that one's going to be 0. Okay. All right. So it's asking us what are the voltages at each of these nodes: VA, VB, and VC. All right. So there is our problem. So the first thing I would recommend doing, let's go by a procedure. All right. So step 1 in the procedure was to decide if we can solve this using methods that we already know, like Ohm's law and voltage divider. And I actually talked about this circuit earlier. We said that, well, we could combine these two in parallel. That's true. We could. But the problem comes after that, because we cannot say that this combined resistance is in series with this, because we can't say that all the current that goes through this combined resistor goes through here. Why? Because some of that current could be going through here. Also, some of the current from here could be going directly through here without going through here. So we cannot say that this is in series with this. So it doesn't work. It breaks down. So we can't use Ohm's law or voltage divider. We're going to have to use some combination of KVL and KCL. Okay, so knowing that, step 2 in our procedure that I wrote down in the first video is to make sure that everything is labeled. So usually lots of things will be labeled in the problem, but make sure we've got everything labeled. So we've got the nodes, all right? And like I said in the last video, we could, there's nothing wrong with defining more nodes than you need. So I could define this as a node, and I could define that as a node, but I don't really need to, because really this is all represented by node B. There's no load between here and here, so really this is still part of node B, even though it doesn't look like it the way we've drawn it. It really is. This is all part of node B, and this is all part of node C, and this is all part of node A over here. So we've got all our nodes taken care of. We don't need any more nodes. We've got all of our components labeled. The last thing that we're going to need, we're going to assume the current flow through all of the loads. All right. I mentioned last time we don't have to assume the current flow through the voltage sources. You don't need to do that, but you do need to assume a current direction through the loads, which is the resistances. Okay, so in this case, two of these were actually given, so there's only one. For I1, you need to just guess, literally just guess, which direction you think the current is going to flow, left to right or right to left. It really doesn't matter. If you guess wrong, it's no problem. It just means that I1 will be a negative value. And if you get that, that is totally fine. Don't go back and change it, because that just makes things more confusing for you and for me as I'm trying to look through your work and understand what you did. So if you get a negative value for current, leave it. Don't go back and change it. That just means that your assumed current direction was actually backwards. All right, so I am going to assume arbitrarily that current is going to go this way through resistor 1, from right to left, okay? Just a wild guess, right? And I'll do all the givens were in black, and I'll do everything else in blue, so you can see what was given and what we're going to do to solve it, all right? So let's fill in what we can. So we already know the value of I2 and I3, so let's fill those in. I2 was 0.1 amps, so go ahead. Everybody should get this part right. Also, I3 was 0.1 amps. And we already know ground, so this is really quite easy also. No calculation necessary to know the voltage at node C, because it's directly connected to ground. So you know immediately the voltage at node C is 0 volts. Okay? So that's everything that was given, all right, but there are some more things we can get really easily. Let's go ahead. So remember, I said that you can use Ohm's law and voltage divider when you can, and in this case there are some places where we can use them, because for R2 and R3 we know R2 and we know I2, and down here we know R3 and we know I3. So if we know those, we can find V2 and V3. So if you don't have to use KVL and KCL, then don't, I guess. All right, so we're going to use Ohm's law. And we're going to write V2 equals I2 R2. I2 is 0.1 amps, and R2 is 20 ohms. So if we're multiplying by 0.1, then we just move the decimal place over, and V2 should equal 2 volts. Yes, V2 equals 2 volts, okay? So, yeah, whenever I come with a significant result, I like to put it in a box. V2 equals 2 volts, then you can write that in. V2 equals 2 volts. Okay, now we can also do the same thing for resistor 3. We can write V3 equals I3 R3. I3 was also 0.1 amps. R3 was 30 ohms. And if we're multiplying 30 times 0.1, just move the decimal place over to the left one, and you get V3 equals 3 volts. So write that in down here, 3 volts. All right, so now we know everything there is to know about resistor 2 and resistor 3. We know their resistance, their current, and their voltage drops. All right. So now, is there anything else that we can do pretty easily? Not that I see right now. Okay, so now we're going to have to look for either loops or nodes where there is exactly one unknown. If it's a loop, then we need to find one unknown voltage drop. For a node, there needs to be one unknown current flow. All right, so I can actually see several different ways to do this problem from here, all right? And it doesn't make any difference which way we do it from here. You'll get the same answers regardless of which way you do it. All right, so think about what we know and what we don't know. All right, it might help to think about what we know. We know everything about R2, its current flow, its voltage drop, and its resistance. And we also know everything about this resistor 3. Our unknowns are this component, and this component, and this component, right? So can we make loops that contain exactly one unknown? And the answer is yes. We can actually make 3 of them. I can, right off the bat, I can see a loop that we could use to solve for V sub L. We could make a loop like this. Or we could make a loop that contains only this unknown by making a loop that goes like this. It doesn't matter if you go clockwise or counterclockwise, although it will change your equation. Your answer won't change. And I can see a way to get a loop with only one unknown being VR. We can make a loop like this, right? So it makes no difference which order we go through. So what I'm going to do is the first one I just said first. So I'm going to write this out. Make it clear what you're doing for yourself and for me. So KVL, write it out like this. KVL, and I'm going to do a lower left loop. Lower left means the lower left loop in the problem. Just kind of describe the loop. Lower left loop. And it's usually helpful if you go in the direction of the arrows. It might make your equation a little bit easier to write. So I'm going to go clockwise in this direction because my arrows are mostly going in that direction. Okay, so I'm going to go clockwise, although it really doesn't matter. It would just change the way your equation looks. Okay, so we're going to do this loop and we're going to go clockwise. And we just got to pick a starting point. And that doesn't matter either. So I'm going to start from C. Why not? I'm going to start from C, and I'm going to go clockwise. All right, so start here and work your way clockwise. We're going to get to the negative sign of the voltage supply first. And remember, for voltage sources, you always take the first sign that you come to. All right, so if I wrote the loop going this way, I would come to the positive side, and I would add VL. But I'm going clockwise, so I'm going this way, so I come to the negative sign first. So my equation is going to be right, negative VL. Okay, then I keep going, and I'm going to go with the direction of assumed current flow through resistor 2, so I'm going to add it. So I go plus V2. And then I'm continuing on, and I'm going with the direction of assumed current flow through resistor 3. So I add V3. And then I get back to my starting position, so I just set it equal to 0. Remember, it's always V's, voltage drops, that you're adding when you're writing KVL loops. All right? KVL is all about voltage drops. KCL is about current flows, but KVL is all about voltage drops. Okay, so I actually know V2 and V3, so I can plug this in. So negative VL plus V2 was 2 volts plus V3 was 3 volts equals 0. Now I have one unknown, and I can solve this. So I add VL to both sides, and I get 2 volts plus 3 volts equals VL. So VL equals 2 volts plus 3 volts gives me 5 volts. All right, you see how I did that? Hopefully that algebra makes sense. So VL equals 5 volts. So I can write that in. VL equals 5 volts. And if you want to, you can go back up here and you can write it in up here, just to remind you that we know that now. All right, so now we know everything there is to know about this and about this and about this. So we need to write an equation, either KVL or KCL. We need to find this and this. All right, so it doesn't matter which one we do first. So I think I'm going to do this loop right here, the upper left loop. And I think I'm going to go counterclockwise just because that's where my arrows are going mostly. And so it'll make it a little bit easier to write the equation if I go this direction. So I can do that because I have a known and an unknown. So one equation, one unknown, I can solve it. KVL equation, upper left loop, and I'm going to go this time counterclockwise. Again, you'll get the same answer regardless of which way you go. Your equation will just look a little different. So I'm going to start from A, and that doesn't really matter either, but you got to pick some place to start. So I'm going to go A and go counterclockwise. So I'm going to go with the arrow. So I'm going to get positive V2 because I'm going with the direction of the arrow. And then I'm going to come around here and I'm going with the direction of assumed flow. That was my assumed direction. So I add this voltage drop, V1. And then I come back to my starting position. So I set it equal to 0. All right, now V2 was known, and V2 was 2 volts, so I can write that in now. 2 volts plus V1 equals 0. So now we're going to get V1 all by itself on one side, so I got to subtract 2 volts from both sides. So I get V1 equals negative 2 volts. All right. I did that on purpose, believe it or not, because I wanted to get a negative voltage drop here so I could show you that it's totally fine and there's nothing wrong with that. So I'm going to write in negative 2 volts right there. Now I know the voltage drop across R1, and I already know the resistance of R1, so I can use Ohm's law to find I1. I1 equals V1 divided by R1. V1 is negative 2 volts, and R1 is 10 ohms. And negative 2 divided by 10 is negative 0.2. And when I take volts divided by ohms, I get amps. All right, so I1 is negative 0.2 amps. All right, so I can write that in. There's nothing wrong with having a negative current flow or a negative voltage drop. Just write it in and leave it like that, and I just want you to know that, okay, what that means is that I assumed the current was flowing right to left, but actually in this circuit, the current is really flowing left to right. But no problem. As long as you know that, then that's fine. I really don't want you to go back and flip the direction because that may have been in one of your previous equations up here. It wasn't in our case, but it may have been in one of your previous equations, and then you'll think, oh, do I need to go back and redo that equation? And you'll probably forget to switch something. So just leave it like it is. Nope, it's not a problem as long as you realize what it means. Okay, so we're almost done here. We know everything there is to know about this one and this one and this one and this one. There's only one thing left really, and that is VR. So I need to make an equation that has only VR as an unknown. And I can do that pretty easily because I can make, well, really, actually, I can do a lot of loops where VR is the only unknown. I could use the whole outside loop. I could do a loop like this. I come up, over, down, back over, and then down, and then over like this. That's a loop. That's fine. That would work. I could also go up, over, down, right. Is that what I just said? Yeah, okay. I could go, okay, here's another one. I could go up to left, and then down, and then left, and then down, and then over. That would be different. Or probably the easiest one, the one I'm going to do, is just this little one right here. I mean, I may as well make it as simple as possible, right? No need to add complexity. So I'm going to do a KVL loop for the right loop. So I'll write R loop. And it's usually easiest if you go with the direction of arrows as much as possible. But you know what? Just to show you, I want to make sure I show you you can do it either way. So you know what? Just for fun, I'm going to go the other direction. I'm going to go clockwise, even though normally I would probably choose the other direction to go with the arrows. But this time I'm going to go clockwise, and it doesn't matter which way I start. Maybe I'll start at C. So I'm going to go from C, I'm going to go this direction clockwise. So I'm going to go against the arrow here. And when I go against the arrow, it's going to be a negative voltage drop. So I'm going to write minus V3, keep on going, there's no lows here, no lows here. It gets to here, and I take the first sign, so I see a positive sign first. So I'm going to say plus VR, then I keep on going, and I come back to my starting position, so I write equals 0. All right, and once again, I know V3 already, it's 3 volts, so I can write negative 3 volts equals VR. Oh, no, sorry. I was thinking one step ahead. No, this is a plus. Negative 3 volts plus VR equals 0. And then this is where we're going to need to flip to the other side. So I'm going to add 3 volts to both sides. So VR equals 3 volts. Okay, and that's it. VR equals 3 volts. And I can write that in up here if I want to. All right, so I know all the components, the currents through them, the voltage drops across them. I got all of that. The only thing left is if I had my multimeter, I want to know what the voltage is. I literally don't know where my multimeter is right now. It's buried under some of the papers on my desk. But here's good enough. So here are the probes for my multimeter, and I want to know what's the voltage drop from A to here. If I had my probes like this, what's the voltage I would read? All right, so the easiest way to do this is to start where the black probe is, and then work your way through the components to get up to here, and find how much voltage you gain as you're going from there. All right, so we'll start from here, which is ground, so we're at 0 volts, and we're going to take the easiest route through here. All right, so the easiest way to get from here to here is through this voltage source. And I know that as I go from here to here, I gain 5 volts because I'm going through the voltage source, and the voltage source steps up the voltage from the negative side to the positive side by, in this case, 5 volts. So from here to here, I gain 5 volts. And this is directly connected to A. All of this is at the same voltage, and that's the voltage at A. All right, so this is pretty easy. Down here, I'm at 0 volts. I gain 5 volts from here to here. So up here, I'm at 5 volts. That's all there is to that. So the voltage at node A must be 5 volts. All right, the voltage at node B is the very last thing that we have to do. This one is just slightly more complicated than the voltage at A. All right, so once again, we're trying to measure the voltage from here to here, the voltage at node B relative to ground. Okay, so the voltage is 0 down here, and I want to know what the voltage is up here. So you know what? There's 2 different ways to get to this. All right, so let me explain both ways, just because you might not always have the option. The easiest way to get from here up to here is to go through the voltage source. So just like before, I know this is all connected. So this is all at 0 volts. And from here to here, I gain whatever this voltage source was, which is 3 volts. So from here to here, I gain 3 volts. So I have the same voltage for this whole section because there's no load between this section up here. So if I'm at 3 volts here, then I'm also at 3 volts here because there's nothing to drop voltage in here. All right, so we know the voltage at node B is going to be 3 volts. All right, that's one way of doing it, probably the easiest way. But let's say I didn't know that. For whatever reason, I didn't have a voltage source over here. There's another way to do it because I know everything about resistor 3. So if my voltage is 0 here, which it is, because it's ground, and all I know is I know the voltage drop, V3. V3 was 3 volts, right? So with the direction of the arrow, I'm going to drop 3 volts from here to here because the arrow is going this way. So my voltage drop is 3 volts from here to here. All right, so I'm at 0 volts here, and I had to drop 3 volts from here to here. All right, so that should tell you what the voltage is here. 0 volts here, and I dropped 3 volts from here to here. So the voltage here must be 3 volts, right? And the voltage here is 3 volts. That means the voltage in this whole area up here must be 3 volts because there's nothing to drop voltage in these wires here. All right, so once again, I'm finding the same answer, which is just kind of a double check. So either way, you can tell that it's 3 volts by going through the voltage source or by knowing that we had to drop 3 volts from here to here, and this is at 0, so this must be 3. Okay, so voltage at node B is 3 volts. All right, so that's it. That completes example 1. I'm going to do another example just because I know this is a new topic and it's good to see several different examples. So let me write out another example. And just like last time, I'll end after I draw out this example. And then in the next video, and the last video for today, I will solve this example. All right, so let's have a circuit like this. All right, that's what our circuit looks like. And your givens, let me give you some nodes also. This is going to be node A. This is going to be node B. This is going to be node C. This is going to be node D. And I'm going to tell you that ground is here. Okay. You know, it happens, and actually both of these examples, it happens that the negative side of these voltage sources is connected to ground, but that cannot necessarily be taken for granted. It's not always true that the negative side of the voltage source is ground, is 0 volts. So don't automatically assume that the negative side here is at 0 volts, and don't assume that over here either. You can only assume that ground is at 0 volts. Oftentimes it will be connected to the negative side of the battery, but not always. Don't assume this is 0 volts just because it's the negative side of the battery. Okay. So those are given, and then I'm going to give you one more thing. I'm going to tell you the current I3 equals 3 amps in this direction. Okay. All right, so you need to find the current and the voltage drops for resistor 1, resistor 2, and resistor 4. And you need to find the voltage drops for all those components. Did I just say current or voltage drops? Anyway, you need to find the current and the voltage drops through all the resistors, and you need to find V sub L, the voltage drop here. All right, so let's write here. I'll go ahead and write out all that you need to find. I1, I2, I3, that's already given, so you can fill that in. I4, and then you need to find V1, V2, V3, V4, VL, VR, and I'll put this over here. And the voltage at node A, the voltage at node B, the voltage at node C, and the voltage at node D, which is given. You should be able to fill that one right in. All right, there's a few things you can fill right in immediately. There's a few things that take just a tiny bit of calculation, and then there are a few things that will take a little bit more calculation. So I will leave you with that. All right, so once again, that's the last example problem that we'll do today. If you can solve that independently, I think you're in pretty good shape. You can probably tackle lab 3 if you can solve this independently. So take a crack at that and think through how you're going to solve each one of those currents and each one of those voltage drops, and we will talk through it in the next video. I'll see you then.